Hi everyone who joined us today with another episode in our training presentations. And today we finally reached the antenna subject in our training course. This will be two concluding episodes, this one and the next one, both covering the antennas. Of course, we are going to apply all the knowledge we gained previously about the propagation properties of radio signals, because all these are related, and this will allow us to better understand the characteristics of the antennas which are going to be discussed today. Before we begin, let me just briefly take a look at the results of the previous quiz test. And I have to admit that the results are quite positive, all in all. But maybe only the last question was a bit controversial, because it stated the following question: in which type of propagation a wave does not follow the curvature of the Earth's surface? And most of you answered correctly, chose the two correct answers. These are skywave propagation and tropospheric scatter. These two definitely doesn't follow the Earth curvature. However, this is not ground propagation for sure, because in the ground propagation the wave follows the curvature of the Earth, but a lot of answers chose the last one, line of sight propagation. And of course, it is not necessarily then during the line of sight propagation the wave follows the curvature of the Earth. It could happen in some certain circumstances, but not always. It can be bent more toward the Earth, so it doesn't necessarily follow the curvature of the Earth. It can be super-refracted, bent downwards. It can be sub-refracted, bent upwards. So in the line of sight propagation, the wave does not necessarily follow the curvature of the Earth, but it could follow. So this answer is not fully inclusive. It could follow under certain conditions. That is why this answer, I consider it to be not correct, because it's not ultimately inclusive. In line of sight propagation, under some circumstances, the wave can follow the curvature of the Earth, but not always. Yes, you don't see the graphs, but I think it's okay, because this is the only question which was a bit controversial, and I already commented about it. The rest was okay. The results are quite good, just some occasional mistakes, but we'll not spend too much time on them. And then we will start the presentation itself. And today we're going to review the main antenna characteristics. And the next episode is going to cover different types of antennas and a bit of history. But this one will be more related to physics and some definitions, let's say. And as an introduction, let me ask you what is antenna exactly, and how it's better to make a definition of an antenna. I like this one. There are many, I guess, but this seems to me the most relevant in terms of the practical consideration. And it states that antennas is the interface between guided wave propagation and unguided wave propagation. The guided wave propagation, I mean the propagation in a transmission line, for example in a waveguide or in a coaxial cable any other transmission line can be as well. So this is the guided propagation in some dedicated medium, in some dedicated line where the signal propagates, and unguided wave propagation, which relates to the free space loss propagation. So the propagation in open space, in vacuum, in the atmosphere of the Earth, doesn't matter. So why do we need antenna? This question can be answered directly judging from this definition. We need the antenna in order to allow our signal to propagate further through the atmosphere or through the space, through the open space. So the antenna is the essential element of radio communications. And the antenna can be characterized by both transmitting mode and receiving mode, because it is transmitting and it is receiving at the same time. So both antennas, if we are speaking about one radio link, then both antennas at both sides are going to transmit and receive. Of course, there are cases when we have only transmitting antenna or only receiving antenna. In case of radio locators, for example, we only want to receive, we surveil the signals which are received. We are not obliged to transmit anything. But in most of the cases, the antennas are both transmitting and receiving. And of course, this is the case of microwave communications, because you usually want to communicate both ways, and to transmit and to receive at the same time. Another important definition and important notion is that antenna is a passive device. It does not amplify anything. So we don't need any power supplied to the antenna in order to amplify the signal or in order to transmit a signal. So basically antenna is just could be a piece of wire, a rod, a dish without any supplied power to it. However, its fundamental characteristic is that it can shape the signal to be stronger in one particular direction. So stronger to one direction than to another. And that is what how we can differentiate between the isotropic radiator and directive antenna. And this is one of the main features of the antenna. Of course, they are omnidirectional antennas as well, but still they are omnidirectional, let's say, only in one plane, for example, in the horizontal plane, while in vertical plane they still have some directivity and they can concentrate energy where do we need it. In that case, we need it in the horizontal plane. And the simplest example of an antenna is a half-wave dipole antenna. And schematically, it can be shown like this, with both electric fields and magnetic fields present there. So we see that this antenna consists of two rods, or a single piece of wire or rod, and we supply our signal to be transmitted to the middle point of this rod, like shown in this schematic. We can see the alternate current which is supplied to this antenna, and we can see changing current and changing voltage on both ends of the rods, of these two rods. It is called half-wave dipole because its physical length, its dimensions are equal to a half of the wavelength to be transmitted. So it is tuned to a particular frequency for transmission. And it's called dipole because it has two poles, one and another, right? And you can see how voltage is changing, the signs on each of the poles. So we have this alternate voltage and alternate current. designated by red and blue accordingly. And we can see that they are varying one at a time, both varying simultaneously, and reach their maxima and minima each at a time, and thus we produce an electromagnetic wave. So we can see that the current is producing the magnetic field while the voltage is producing the electric field, and these two alternating fields is what forms an electromagnetic radiation. And that is how we use the antenna as an interface between our line signal and the free space signal. We allow to produce an electromagnetic wave and to propagate it further, to be received somewhere else. And here, this type of antenna, as well as any other antenna, is characterized by input impedance, which consists of the active and the reactive part. We are going to see this on our next slide. But what is necessary is that we can affect this impedance by selecting a feed point, for example, and by selecting a dimension of the antenna. What does it mean? That means that the feed point selection is usually chosen in order to minimize the impedance of the antenna, because we want it to be as low as possible for better power transfer, for better signal transfer through this antenna to the open space. That is why, for example, for the dipole antenna, simple dipole antenna, usually we select the middle point. Why? Because, as you can see from this schematic, the current is at its peak in the middle of this antenna. And according to Ohm's law, if the current is maximum, then we have the minimum impedance, minimum resistance. Impedance is the same term as the resistance, basically. So we have the minimum resistance at this point, and we can drive our signal directly to this point of the antenna. And speaking about dimensions, it all depends on the signal frequency to be transmitted, as I mentioned, because it depends on the wavelength. And for the dipole antenna, if we choose this antenna to be at the same dimension as a half of the wavelength, right? Then we are going to minimize the reactive part of the impedance, because the energy stored in the near field of the antenna, both magnetic and electric energy, they are going to be equal, and a condition of resonance will occur. They will compensate each other, and our reactive part of impedance will be equal to 0, which will be beneficial for matching this antenna with a driving signal, with the transmitter. And let me explain this in greater detail further with the equivalent circuits. We introduced the equivalent circuits in order to examine the parameters of the antenna and to make some relations between different parameters of the antenna. Also, we would like to depict the resistances and reactances of the antenna, also with the purpose of optimizing the design of the antenna. And as I mentioned, it is important to take into account antenna duality. It is both the transmitting element and the receiving element. So we have separate equivalent circuits for transmitter and for receiver. This one is for the transmitter, and you can see the transmitter itself inside a triangle with a driving signal Vs with some source resistance, and what comes further is related to the antenna itself. It is the reactive resistance and active resistance. So for comprising together the impedance, right? So the impedance denoted by Z consists of the active part and reactive part. And active part in turn consists of radiation resistance and loss resistance. So radiation resistance actually defines how much power do we transmit as energy in the form of the electromagnetic radiation. So how much energy do we actually radiate with the antenna or transmit to the open space, while the loss resistance defines how much power do we lose as a thermal loss, as a heat. So we heat up antenna because of this power loss at the element itself, and we actually lose this part of power in the resistance, in the loss resistance. So this part of resistance is somewhat negative to us, undesirable to us, and we want to maintain it as low as possible. So the current is distributed between this radiation resistance and loss resistance. And we want to keep the loss resistance as low as possible in order to dissipate less power through this loss resistance, which is converted to heat. And again, as the receiving part, we can draw a schematic like this, with the receiver on the left, with its load resistance, and with the reactive resistance again of the antenna, and active resistance of the antenna. Similarly, consisting of the radiation resistance and loss resistance. And here, additionally, we introduce a notion of noise temperature, which accounts for the noise present on the output terminals of the antenna. And this noise temperature actually is the measure of the noise power, of the noise power density of the antenna. And this is some noisy element which also is undesirable for us. And here we have another symbol of V signal. This is the signal which drives the antenna, which is received by the antenna, and which is transferred further to the receiver load. So what do we want to maintain for the receiving equivalent circuit? We want to make sure that the radiation resistance is larger than the loss resistance, much larger than this. In that case, most of the power is going to be spent on radiating, on transmitting the signal, on producing electromagnetic wave. And less power will be dissipated as a heat through the antenna. So this is our main condition for the transmitting antenna. And for the receiving antenna, we want it to match the output, in this case, the input impedance of the transmitter and of the receiver, sorry. So here how it looks like in terms of the formulas. So we want the perfect match between the antenna and the transmitter or receiver. This is true also for the transmitting equivalent circuit. So here we want to achieve that the radiation resistance is equal to the source resistance in case of the transmitter equivalent circuit, and equal to the load resistance in case of receiver equivalent circuit. And this is called matching of the antenna impedance with impedance of the receiver or transmitter. So we want to maintain this for both cases. And for achieving this goal, we also want to minimize this reactance. because this is something which is undesirable for the antenna parameters. Reactance can be inductive or conductive, so either one or another. And we want to minimize this, because this is going to introduce some parasitic currents, parasitic voltages through the antenna, unnecessary noise, unnecessary loss of power. So we want to minimize this reactance. We want, in a perfect case, it to be zero. And in that case, we are going to achieve perfect matching between the antenna and the receiver or transmitter. So these are main conditions for both transmitting circuit and receiving equivalent circuit. The first one is that radiation resistance is larger than the loss resistance. The second is there is a matching between the antenna and transmitter or receiver. And this assumes that the active resistance is equal or almost equal between the antenna and the transmitter or receiver, and the reactive resistance is equal to zero. So these three conditions have to be maintained. All right, now let us get to the second important notion of the antenna, so-called aperture. And then we also will examine what is the gain of antenna and how it is related to the aperture. So let us get back to one of the first presentations when we discussed the isotropic radiator, and imagine again this perfect abstraction, this mathematical or physical abstraction of the isotropic radiator hanging somewhere in the space and producing some electromagnetic field around it, transmitting this field to the outer space, to the space. And as we know already, gain of isotropic radiator is 0 dBi, because it's not directed to any particular direction, right? It's not concentrating the power. It is distributing the power evenly to all the sides, in a form of a sphere. So we imagine this, and then we're going to introduce the isotropic power density notion. So this is going to be at some time instance during the radiation and at some distance from this isotropic radiator point. So we have a distance, we have a particular isotropic power density at some point related to this area of the sphere. And we have this power of our transmitter, which drives this isotropic radiator. And in the same manner, we have a receiving part of our system, and we have this receiving part of the antenna characterized by the effective surface area. So we transmit, and we characterize this by the power density of the transmitting point of the transmitter, and we receive, and we characterize this by the effective surface area of antenna. And in order to find the relation between these parameters, we introduce, of course, the area of the sphere, which is equal to 4p d squared. And from this we get the isotropic power density. We relate the overall power which is supplied to the radiator. We divide it by the area of the sphere, so we find out our isotropic power density at a particular point in a space and at a particular time instance. Also, we introduce a parameter called the effective surface area of the isotropic radiator, and this will be lambda squared divided by 4p by the definition. And this relates to the isotropic antenna. This perfect physical abstraction. So if we combine the two, we must combine the transmitting part and the receiving part. So we multiply one by another. We multiply this isotropic power density by the receiving area of the antenna, which is also called aperture, by the way. That is why it is designated by A. And when we multiply, we get this relation. And if you remember, from this relation, we obtained the Fresnel equation, one of the basic equations for the radio communications. But this time, we are going to go different way. We are going to leave this aside. This was just a reminder of how do we find the resulting received power in these terms. But we are going to review this notion of aperture separately. And what is that, and why does it matter to us? And if we go from this physical abstraction to the real case scenario, to the real antenna with its directivity, its certain parameters, this is no longer the isotropic radiator. And we cannot find the aperture as defined here by lambda squared divided by 4p. Instead, we introduce another coefficient denoted by g, and this coefficient is called gain of the antenna. And this represents the actual parameter of the actual antenna, real-world antenna. We can see that this parameter, this aperture, depends on two angles. The first one is the elevation angle, and the second is the azimuth angle. Both these angles are going to help us to relate to particular direction. So they help us to find the direction in which the propagation is stronger, for example, and which defines the directivity of the antenna. At the same time, this coefficient denoted by g, what is called actually gain of the antenna, is also dependent on the elevation and azimuth angles. So this gain, this coefficient, is dependent on the direction in space, which can be characterized by two angles, theta and phi. This is the gain of our antenna. So this is one of the definitions. Gain is what makes difference between the isotropic radiator and the real antenna, and it defines in which direction, depending on the elevation and azimuth angles, do this antenna concentrate power more efficiently. So in which direction does it send the signal with a higher gain. Okay, and now when we derived to this notion of gain, to this parameter, let us relate this parameter to another parameters which are dependent. All are interdependent, and these parameters are directivity and efficiency of the antenna. So the gain can be described in different ways. The first way I just presented shows how it makes difference between the isotropic radiator and the real antenna. So this is some kind of coefficient in case of describing it as an aperture. We have a notion of aperture, and we have gain as a coefficient which represents the directivity of the antenna. So in order to be clear, let us define the aperture as well. An aperture denoted by IA represents the amount of electrical area an antenna presents to an oncoming electromagnetic wave. This aperture is not directly related to the dimensions, physical dimensions of the antenna. So this is not a physical parameter. This is electrical parameter. An aperture is not equal to the, let's say, the area of the antenna, of the receiving antenna. or the dimensions, the overall dimensions of the antenna. This is related to the electrical parameters and can be defined as the following, as we just learned. By using this coefficient, which is gain, G, depending on theta and phi, two angles in a space. Again, the gain of this coefficient can be further described as the parameter which combines the antenna's directivity and radiation efficiency. So this is a complex value. This is not just a simple value by itself, defined by itself, but it consists of two parts. The first part is the directivity, and the second part is the efficiency. Efficiency is denoted by eta and directivity by d, which is also dependent on two angles, on the elevation and on the azimuth. So we can define gain as the multiplication of antenna's efficiency and directivity. And we will go further to define what is directivity. And the directivity is the ratio of the maximum radiation intensity to its average value over a sphere. So again, we compare the real actual antenna to the isotropic radiator. But in this case, we compare the radiation intensity in the particular direction. And most of the time we're speaking about the antennas which have this, the single maximum of this maximum radiation intensity, right? So there is a single point over the sphere around the antenna which is going to be selected as a maximum. And if we take this radiation intensity at that point where the gain is maximum of the antenna, and if we relate it to the average value of the radiated power over a sphere around the antenna, so some average value all around the antenna, then we get this directivity notion. It is also dependent on both angles, of course, because we assume this parameter to be three-dimensional over the sphere, so it can be directed to any direction, but we will find it just like that. We were going to relate it to the average value over a sphere of the radiation intensity, designated by U. And it's worth mentioning that this radiation intensity is just the power of a signal to a solid angle. The solid angle is the angle in space, three-dimensional angle, let's say. So this can be imagined as a cone, as a measure of the amount of the field of view from a particular point. So this is like an angle, but in three-dimensional space. And if we divide the overall power over this angle, which is expressed in steradians, then we find this radiation intensity. And finally, the efficiency of the antenna, which is dependent on different parameters, can be defined as the radiated power related to the overall accepted power. So we have our transmitter and we have our antenna. Antenna is driven by the transmitter. So we transfer our signal power to the antenna. And some part, the most part, actually, of this power is being transmitted as the electromagnetic wave. So this is called the radiated power. And if we divide this radiated power to the overall power which we supply to the antenna, then we will get this efficiency of the antenna. And here again we meet with these two resistance, with these two types of an active resistance: radiation resistance and loss resistance. And here the power is described in these terms. We can see that our current I is divided through this, is the same for the radiation resistance and for the loss resistance, because they are connected in series, right? So the current is the same, and this current represents our transmitting signal, the power of our transmitting signal. And the power will be current squared multiplied by the resistance. So we can see this in this relation, the smaller the loss resistance gets, the better is the efficiency of the antenna. So in perfect conditions, the efficiency of the antenna is 1. This is a dimensionless unitless parameter with its maximum value of 1. So in perfect conditions, we have no loss resistance, it is 0, and we divide radiation resistance by itself, we get 1. This is the maximum we can achieve from the antenna, the maximum efficiency of the antenna. But in a real-world scenario, of course, we will have some losses dissipated as a heat, but we want these losses and this loss resistance to be as minimal as possible. And if we are speaking about the isotropic source of radiation, then the aperture will have this value, lambda squared divided by 4p. So this gain coefficient becomes 1 or 0 dBi. So if this is a unitless parameter, then we refer to it as 1, a unity, as in the case of defining aperture. So we're not multiplying by anything. We don't have this coefficient anymore. It is equal to 1 if it is unitless. If we express gain in dBi, so related to the isotropic radiator, perfect isotropic radiator, then this gain becomes 0 dBi for the isotropic radiator. Anything that is larger than 0 will be related to the actual antenna, real-world antenna. And the directivity of the isotropic radiator is equal to 1, because it doesn't have any particular direction of radiation. It radiates over the sphere to all the sides of the sphere evenly. So it's equal to 1. And the good example of an antenna is when the efficiency is close to 1. In the perfect conditions, it would be 1, but of course, in a real scenario, we will have a bit less efficiency of the antenna. All right, and here how it looks like in terms of the radiation pattern. The upper image shows you the isotropic radiator with a gain of 0 dBi, and the lower part of this picture shows you non-isotropic radiator with a gain which is larger. So this is real antenna, and you can see that it has some particular direction of transmission of the signal, of radiation. In this so-called main lobe, it will radiate more energy, and less energy is distributed to the other sides of the antenna. So we are going to, antenna doesn't amplify anything, it just directs the signal. So it takes the signal from other sides and it concentrates it to the larger beam in the main direction. Please let me show this as an example with a flashlight, in order to better understand such notion as the side lobes and main lobe. So here we have the isotropic radiator, right? So it evenly distributes the power over the sphere around it. Of course, now we are seeing the two-dimensional picture, but we can imagine this as a three-dimensional picture as well. What happens if we have the real antenna with some gain which is more than 0 dBi, which have some directivity. Then we have something like this. We have a main beam, main lobe, where the most of the energy is transmitted. And this is represented by this brighter spot on the wall. We have this main lobe here, and we have some side lobes as well. This antenna doesn't perfectly concentrates all the energy in the main lobe. It also distributes a bit of energy around it. And this is what we see here as the side lobes. Also, we can say that somewhere in here we have a half power beamwidth, but we will discuss it a bit later. So this all depends on the parameters of the antenna, how well it concentrates the signal, right? It can concentrate it better, it be narrow band antenna, or a bit worse, and it can have also a so-called back lobe, right? So it can also send some signal on the back side of the antenna. But mainly it has some particular direction, and it represents the main lobe as well. Well, let's see how we can depict this schematically and how we can relate it to the antenna itself. But first, let us introduce these units. What is dBi and how it can be expressed mathematically. So dBi is antenna gain expressed related to the isotropic source of radiation. So we will divide our power in this particular direction, which we choose to describe the gain of the antenna. Basically, this is the main lobe of the antenna. It is what we see here in the primary direction of transmission. And we divide it to the isotropic radiator power in the same direction. And we convert this to logarithmic scale and multiply it by 10 to obtain the dBi notion. Also, alternatively, we can select an ideal half-wave dipole as a base for our conversion, for our relation. So we divide the power transmitted in the main lobe of our antenna by the power transmitted by the analogous perfect dipole, half-wave dipole antenna, which is denoted by this P. And in the same terms, we obtain another measurement units of dBd, or antenna gain related to the half-wave dipole antenna. So this is our two main notions, but most of the time we are using dBi, of course. So as I showed you in this example, directive antenna broadcasts more energy than the isotropic one in some directions. So we saw two different pictures. We saw this evenly distributed radiated power to all directions, or we saw this concentrated beam of the flashlight on the wall. And this represents the directive antenna. So it sacrifices the power from all other parts in order to direct this power to the main lobe. And from here we can define what is the half power beamwidth, which is very important parameter for describing the antenna, for describing the directivity of the antenna. This is very important parameter also for radio engineers in order to describe how well the power from the antenna is concentrated and how well it is directed. This is very important for link planners, for avoiding the interference cases, etc. So we can define it as the width of the main lobe at half power intensity. So this will be the main lobe definition, and the degrees of the main lobe exceeding which we are going to lose half of the power intensity. So we are going to lose 3 decibels, or 3 decibels below the bore side gain. And the half power beamwidth parameter depends on the frequency. Typically, if we go higher in frequency, the beamwidth becomes narrower. As we see for the E-band, for example, 80 gigahertz microwave antennas, they are extremely narrow beamed. They have extremely narrow beamwidth. That is why it is very difficult to align them. Also, for the bigger antennas, we have narrower beamwidth as well. So it becomes more difficult to align the bigger antennas than the smaller antennas. And the side lobes, which we have and which we also saw on the wall, represented by the flashlight, is the result of concentrating most of the energy in the main lobe. So we concentrate this energy to the main lobe, but we have some power left. We cannot perfectly maintain this main lobe without any side lobes, and we still have some, let's say, unwanted or undesirable emissions through the side lobes. And also we have some energy which is transmitted backwards of the antenna. In order to describe this parameter, we use the notion of front to back ratio of the antenna. And this is the ratio of the gain in the desired direction to the gain of the opposite direction. Usually it is quite a big amount of more than 60 decibels. So we are sure that we don't produce any interference in other directions. So we concentrate our power where it should be transmitted. And the backside of the antenna doesn't receive a lot of transmitted power. And also we can show this kind of a diagram which represents half power beamwidth related to our main lobe. This is our maximum direction of the main lobe, and here our gain will be the maximum gain. And actually, if we are speaking about the gain of the antenna, then we are speaking about this value right here. This is our maximum. And from here, we obtain the notion of the half power beamwidth, where the power becomes reduced by half, or by 3 decibels. And this angle is called the half power beamwidth. And we have our main lobe as well as our minor lobes or side lobes, and also sometimes we have a back lobes here. All this together comprises what we called the radiation pattern envelope, which you can see here. Basically, this is the same, just with the designation of degrees, in this case in the azimuthal plane, but also it can be shown in the elevation plane. So basically we can have 2 radiation patterns, one in the azimuth and the second is in elevation. Both of them can be combined and we can obtain the 3-dimensional picture of how the antenna distributes the energy around itself. And of course, we can evaluate how much energy is sent in the desired direction and how is distributed through the side lobes and back lobes. There are some examples of the radiation pattern envelopes which are given by the antenna manufacturers. We're not going to review them now, but microwave engineers, of course, are familiar with these diagrams, which represents you the radiation pattern in azimuthal plane and in elevation plane, and which are going to show you not only the half power beamwidth or the gain reduction in any direction away from the main lobe, from the main direction, but also you can see there such parameters as the cross-polar discrimination, or XPD, This is this parameter describes how effectively antenna cancels the signal of the opposite polarization in a particular direction. So if the antenna is meant to receive the vertically polarized signal, and if it accidentally receives the horizontally polarized signal, this is the amount of gain reduction which is going to be achieved by this antenna for this oppositely polarized signal. And this is called the cross-polar discrimination, which can be also derived from this radiation pattern envelopes, because we have these characteristics in both vertically polarized signal and horizontally polarized signal. Also, if we have a cross-polarization, or if the antenna is supposed to receive in vertical and the signal is obtained in horizontal, and vice versa. Also, we can see the front-to-back ratio. If we look at the radiation pattern envelope on the back of the antenna, which is 180 degrees away from the main lobe, we can see how much the gain of the antenna is reduced. And this is called the front-to-back ratio. And we can evaluate the side lobe suppression, how much the signal is suppressed in the direction of the side lobes comparing to the main lobe. And as I mentioned, by combining these two planes, the azimuthal plane and the elevation plane, we can, of course, construct the three-dimensional radiation pattern of the antenna. But this is very convenient to view it in some kind of the software rather on the paper. So on the paper, in the documentation, we usually use the two-dimensional picture in two planes, azimuthal plane and elevation plane. But in the simulation software, we can produce something like you see on the screen now, this three-dimensional picture here. Sorry, somehow I skipped all my slides. Let us get back to the next slide. And we're going to describe the next parameter of VSWR, or voltage standing wave ratio. This is another important parameter of the antenna, and it has something to do with the reflections. So let us imagine the system of the radio or transmitter and the antenna. The transmission line is in between. And we can imagine three ways of the signal traveling between the antenna and radio. Our direct signal, denoted by this blue line here, blue arrow. Reflected signal. Why do reflections occur? Because of the impedance mismatch between the radio and antenna. There could be some irregularities in the transmission line or in the feeder of the antenna, how it is connected to the antenna. There could be some water ingress, there could be just physical damage, there could be poor design of the antenna itself, of the transmission line itself. And because of all these things, we don't have the perfect match of the impedance between the radio and the antenna. And the transmission line is not perfectly matched. That is why we have reflection of some power from the antenna to the radio, back to the radio. We can imagine that the energy of the transmitted signal is bounced off the antenna and gets back to the radio, which of course is undesirable effect, and we have to avoid it. But we will always have it to some extent in the real conditions. We don't have anything perfect in this world, so the antenna is not perfect as well. It has some design limitations. That is why it is important to characterize it by the so-called voltage standing wave ratio. So we'll have the direct signal, the reflected signal, and the delayed signal, the echo, which is going to be sent back to the antenna. And of course, this is going to produce some unwanted effects on our signal. We don't want this. And we want to minimize this effect. But in order to understand how much does it affect our signal, we introduce this parameter. And this parameter, I forgot to mention that in this case, when the signal is reflected back, we can observe a phenomenon which is called a standing wave, or a wave forming between two parts of a transmission line. If this is a closed transmission line, let's say. If the signal gets back to the source, then we can observe the formation of the standing wave. A simple example of a physical standing wave is oscillation of a guitar string, for example. There is a standing waves because the string is fixed at both points and it oscillates. So it sends the signal back, and this bounced oscillation is going to interfere with our forward oscillation, and this is going to form the oscillating pattern of the standing wave. So the standing wave oscillates in time, but its peak amplitude profile does not move in space. In the formula, we can define it as the maximum amplitude, voltage amplitude to the minimum voltage amplitude after the standing wave is being formed in this system. Let me show you how it looks like. So, we have our direct wave, right, with a certain amplitude. This will be our direct wave. And let's imagine that we don't have the perfect match between the transmitter and the antenna. So we have some reflected power gets back from the antenna to the receiver, to the transmitter. So we have also the reflected wave. And the direct wave, together with the reflected wave, are going to produce the oscillating standing wave in this system. And let's say that we have some part of the energy bounced back from the antenna. Not all of this. Some part of the energy was successfully transmitted in the air, in the space, but some part of the energy returned back. So the amplitude of this energy will be smaller than the initial forward wave. And it will be something like this, for example. And this reflected wave can have different phase delay comparing to our main signal or forward signal. So in this case, there is no phase delay. They are perfectly in phase. In this case, we'll have something that is called the constructive interference, like we observed in one of the previous lectures. In this case, we will have the resulted wave, which is stronger. So we add this value to this and produce something like this. This is the combination of the forward wave and the reflected wave. And we can say that this maximum, let's call it maximum wave, because in this case the constructive interference will result in the maximum amplitude of our overall signal, right? So this maximum amplitude is going to be the combination of our forward signal, initial signal, and our reflected signal, VR. This will be our maximum case. And if this reflected wave will be perfectly out of phase or shifted in phase, like this, Then we will have our minimum combined signal. And then in this case, we are going to subtract this signal from this signal. This will be perfectly destructive interference case. And we will have our resulting signal. Let's select the same color, but draw it like this. So at this point, we will have the minimum amplitude, which is possible in this standing wave. So this will be perfectly destructive interference, and this will be perfectly constructive interference. And this difference between the two is what we are going to use to express our voltage wave standing ratio. So this minimum condition goes like this: the forward amplitude and subtracting the reflected signal amplitude. Okay, and in this case we just saw what we get here. What is voltage standing wave ratio? This will be the relation between this maximum amplitude case, right, and the minimum. And in perfect conditions, this is equal to 1. So this is the perfect case, when voltage standing wave ratio is equal to 1. Why? Let us see. Let's say that there is a worst case, when all of the power is reflected back to the transmitter. So actually it cannot happen in real life, but let us imagine this will be our worst case, our nightmare. In this case, this reflected signal is equal to the forward signal. And we will have some value here, which is 2 times forward signal, and we will have 0 here, because we subtract. And if we divide by 0, then we theoretically, mathematically have an infinity. So infinity is our worst voltage standing wave ratio. But actually, in poorly designed systems, for poorly designed antennas, it can reach some values, not infinity, but some very high values. And under perfect conditions, we have no reflections at all. So this part disappears. We don't have this reflected signal anymore. It is equal to 0 here, right? We have only initial forward signal. In this case, according to this formula, we will have 1, because we just divide forward signal amplitude by itself. So this is our perfect case. And some typical case for real antennas could be around 1.2. Could be less than this, could be more than this, but this is some realistic, more or less realistic example. Okay, so now let's get back to this voltage standing wave ratio. I hope that it became clearer for you. What does it represent? And just to show you some other ways of representing this value, there is also a reflection coefficient. And the reflection coefficient is the opposite interpretation of this scenario. In perfect conditions, it's equal to 0, and in the worst case, it's equal to 1. But it can be also converted using the voltage standing wave ratio, or it can be expressed as the relation between the returned power amplitude and the forward power. Return signal amplitude and the forward signal amplitude, as you can see on this formula. Another term which sometimes is used in the data sheets of the antennas is the return loss, and it is expressed in decibels, and goes as the 20 logarithm of 1 divided by the reflection coefficient. As I mentioned, the perfect case of the antenna is when voltage standing wave ratio is close to 1, and the good return loss is considered to be more than 20 decibels. Yes, and this is how we can represent the standing wave formation in our transmission line. So this is how the standing wave is being formed. This is actually the case of interference, either constructive or destructive. And this red curve is the standing wave, which is formed when the forward wave and the return wave coincide and either amplify each other or cancel each other. And further, let's speak about the polarization and cross-polar discrimination, which I already mentioned. And the polarization of the antenna is mainly defined by the radiating element of feeder positioning. So in some cases, this is a waveguide which defines the polarization. For example, in the parabolic antennas, which are very often used for the microwave transmission, this is a waveguide which serves as the feeder of the signal for the antenna, and the orientation of this waveguide is going to define which polarization is this, vertical or horizontal. Usually the same polarization must be set for both sides of the link, the transmitting part and the receiving part, so that we have this match between the transmitting signal and the receiving signal, and that we have this maximum power transfer. In another case, when we have this mismatch, when the signal to be received doesn't match the antenna orientation or the waveguide orientation, we have something that is called cross-polar discrimination comes into play. So this is the amount by which the signal is attenuated if it is received with the opposite polarization. Sometimes it is beneficial if we want to cancel the unnecessary signal, unwanted signal, the interfering signals. But if we are planning our own communication line, then of course the polarization between the transmitter and the receiver must match between each other. And here are the example of two waveguides shown on this picture. And each of these positions define the polarization of the signal to be transmitted. So the question to you is which picture corresponds to vertical and which picture corresponds to the horizontal polarization? What do you think? So if you are still watching and if you are have some ideas, please write here in the comments what is representing, which polarization is represented by the left waveguide position and which polarization is represented by the right waveguide position. You can imagine that these are the openings of the waveguides which drives the antenna, which transfer the electromagnetic energy to the antenna feeder. So we feed our transmitted signal to the antenna through these waveguides. And this waveguide can be oriented either horizontally, like on the left, or vertically, like on the right. So please write your suggestions. What do you think? Which position of the waveguide corresponds to which polarization? Of course, there are also different type of polarization, slant polarization, circle polarization, but most of the time, if we are speaking about the microwaves, we're referring to this either vertical or horizontal polarization. Okay, I hope that somebody is watching us today between the Christmas and the New Year Somebody's still alive and somebody is still interested in the microwaves. Okay, we have an answer, and I think it was meant, yes, and the second answer confirmed this. As per the suggestion, the left corresponds to vertical and the right to horizontal, and this is the correct answer. This is counterintuitive, of course, because the position of the flange itself is different. But actually, yes, the left side represents the vertical, while the right side represents the horizontal polarization. That's correct. And finally, we are going to speak about the near field and far field. We already referred to the subject when we were speaking about the free space loss. And we defined that the free space loss, we determined that the free space loss can be only calculated in the far field of the antenna. The same applies to the gain. So we can use the notion of gain, the gain parameter, only referring to the far field of the antenna. And we can find out the free space loss of the signal in the far field only. And this is an interesting picture which you see on the screen now, because it shows you the distribution of the electromagnetic field around the dipole antenna. So we can see the same dipole antenna which we saw in the beginning of the presentation, consisting of two rods and having this middle point when we feed our signal, our power. This middle point is called here an equatorial plane, right? And we can see the near field distribution of the power here. It's quite interesting because it's not like anything would radiate power in one direction outwards from the antenna. Instead, there are some unusual field distribution which is having place here. So we cannot speak about any particular field power in this part of the antenna, far from the antenna. We cannot speak about this power density or gain or free space loss until we reach this boundary sphere, until we reach this place where the near field becomes the far field. Near field ends and the far field begins. And this is the far field is represented here by the radiated energy flow, and it starts only from this boundary sphere. And before that, there is the particular fields distribution which is not really well defined for us, which of course we can define with some sophisticated mathematical model, but it's not that easy. It's not an easy task. So we don't want to, and still it doesn't matter what happens there, right? Because we always transmit to some greater distance. So we want to know what is 100 meters away, 1 kilometer away, 10 kilometers away, etc. And this is where we already dealing with a far field, and where we can define our antenna gain, where we can define our free space loss. And the far field distance is dependent on the wavelength of the signal to be transmitted, or on the frequency to be transmitted, and on the maximum dimensions of the antenna in meters here. According to this formula, it is expressed in meters. And for the dipole, this will be the half wave of the signal, so the dimensions of the dipole. For the parabolic antenna, it's going to be the diameter of the antenna, etc. If we look into the near field and try to represent what happens there, then it will be not that easy, and we can describe the behavior of the signal in terms of different parameters. For example, we can describe it as a gain reduction. So there will be our gain of the antenna, which is defined in the far field, but reduced by some amount. And this amount is going to be dependent on the far field of the antenna, on its dimensions and on the signal to be transmitted. So here's a graph which shows that the antenna gain is going to be reduced in the near field, and how much is going to be reduced. And also, this graph shows you that the power density is uneven there, and it can be variable. It varies in certain limits, also depending on the dimensions of the antenna, on the signal to be transmitted. But the power density is also something that cannot be easily defined within the far field, within the near field. So we're using the far field notion for all our calculations for the gain definition of the antenna, and it could be only an academic interest to try to represent what happens in the near field. For us, for the radio communication engineers, for the microwave link planners, most of the time we want to know what's happening in the far field distance. That is why, but it is very important to define where the far field starts, especially for some larger antennas and for some lower frequencies, when the far field can be extended to the significant distance away from the antenna. Okay, that's all for my side. If you have any questions, please mention them in the comment section now or later. I can answer them now, or I can answer them later as well. If you don't have any particular questions as for now, then please take a chance with our control quiz, which you can find in the link below. And we're going to meet once again in the new year with our concluding episode on the antennas. But for now, I'm wishing you Happy New Year, and we'll see you next year. Goodbye.